Hello, in this video I'm going to talk a little about nuclear fusion reactors. So this is technology that's still in its infancy, really. The scientists haven't cracked these yet. They've been able to create fusion, but not create a reactor that is sort of viable commercially, as in it's going to produce more energy than is required in order to build it and run it. So we know that nuclear fusion is the driving process inside stars, and yeah, that produces an enormous amount of energy, and it can produce a lot more energy for generally safer waste products than nuclear fission. But whereas we've, as a species, have managed to create fission reactors, which are the nuclear power plants that are all around the world, no one's managed to create a commercially viable fusion reactor. So I'm going to talk a little bit about what the state of play is with these fusion reactors at the moment. So as I say, a little bit of the background with nuclear fusion, this is the process that goes on inside stars. You need a very high temperature, pressure, and what's called a confinement time, as in being able to keep the reacting particles close enough together, to keep them in this high temperature, high pressure zone so that they might fuse. We've got this problem of getting within the range of the strong interaction. So we need to get to around about 10 to the minus 15 meters as separation of these nucleons. You need to get them that close. And of course, in the case of two protons, they're going to be repelling each other due to the electromagnetic interaction. So we've got electromagnetic repulsion, but we need to get into this range where the strong interaction can then bind things together. Now, that isn't particularly easy. That's why we need this really high energy environment. Now, in stars, this is mostly protons. When we get onto the astrophysics section of these videos, we'll be looking at the proton-proton chain, one of the mechanisms where these protons, these hydrogen nuclei, are binding together in order to form heavier elements. It goes through multiple stages. But these are really your 1-1s. These are just protons here. It's a little bit easier to get deuterium and tritium. So deuterium is hydrogen with an extra neutron, and tritium is with two extra neutrons. So we've got a neutron and a proton here, and we've got two neutrons and a proton for tritium. Now it's a little bit easier to get these to fuse. You're not adding to the electromagnetic repulsion, but you are adding to the strong attraction. So they react more easily, but we still have to get temperatures up to around about 10 to the 8 Kelvin, so 100 million degrees Kelvin. So that's pretty hot. We've also got an issue that tritium is relatively rare, because the half-life of tritium is around about 12 years. So it's not like there's loads of tritium kicking around, so that needs to be produced alongside any fusion reactor. As I say, the output of this is generally going to be safer. It's going to have lower radioactivity. There's less waste. There's plenty of fuel, at least in theory. I mean, there's no shortage of hydrogen around that we can get our hands on. But so yeah, it's easier to get that, maybe, compared to enriched uranium and such like that's used in the fission reactors. But it is very, very difficult, and there are other problems, such as managing neutrons that come out. If you get some reaction that, say, we've combined a tritium and a deuterium together in order to create a helium nucleus, then we're also going to get a neutron. I mean, you can see these numbers have to add up as usual. So we've got 5 here, 5 there on either side of this reaction, and a 2 and a 2. So we've got this neutron has come out. And managing these neutrons can be difficult. I mean, they have the plus side that you can get them to interact. These have shot out. They're carrying a lot of energy with them. So you want to capture that energy in some way. You can get them to react with, say, lithium in order to produce more tritium, which can then be fed back in to continue the process. So that can be useful. But having all of these neutrons flying around with high energy, it can degrade the structure of the reactor itself, and it can create, other radioactive properties and radioactive products of the reactions. So it's not like everything is just wonderful and straightforward in terms of the actual process. If it can be actually started to run, there are still some issues, but there aren't the issues of having this epically radioactive plutonium or other such things that are produced by the fission reactors. Although, as I mentioned in the video on fission reactors, the amount of waste that's produced by those, now that they're so much more efficient, is reducing all the time, but it's still an issue. So let's have a look then at the types of fusion reactors that are kicking around at the moment. There's two main types. So there's the magnetic confinement fusion. So magnetic confinement, as the name is suggesting, is you get this plasma, which is the stuff that we want in a fuse. So we get a plasma of deuterium and tritium, and we're going to contain this using magnetic fields. So you have a whole load of magnets kicking around. It creates what ends up being this sort of donut-shaped plasma, which seems to be one of the more stable configurations from the plasma. So you end up with this weird sort of donut of plasma held in place by magnetic fields, and you need it isolated, because if that's interacting too much with the surroundings, then of course all of this high temperature, high pressure that you're building up in here, it all gets released and then the plasma disappears. So you need it confined, and this is one of the real challenges of setting up these fusion reactors. So yeah, you have something like this set up. This is they're also called tokamak. So tokamak reactors. This is a acronym that came out of the Soviet Union. So the Soviet Union in the 1950s came up with this idea of this magnetic confinement, and yeah, there's some Russian description behind what tokamak means. I don't know what it is, but the name sort of hangs around this Russian underpinning for a lot of this. But it's still popular. I mean, obviously no one's cracked how to do it. The ITER project that's currently going on in the south of France, the International Thermonuclear Experimental Reactor. That's what this is standing for. Plus, of course, it also means like the way or the path or something like that in Latin, however you want to interpret it. So it's got one of these nice double meanings that people like for a lot of these things. And this ITER project is located in the south of France, but that doesn't mean it's entirely a French project. A bit like CERN is not entirely run and controlled by the French and the Swiss. This is an international project, exactly as the I is saying in ITER. And they're getting to the stage where they can have brief periods of producing more energy than is required to initiate the process. So they can create the plasma and get some fusion happening, and the amount of energy that comes out is more than the energy required to create that plasma. Of course, there's a lot more to it than that in order to get a viable commercial fusion reactor, because you have to build the reactor as well and plug it into things and all the rest of it. There's an enormous amount of energy that goes into actually just creating the thing itself. So you need to factor all of that into it. So there's a lot of other energy that needs to be taken into account when you're deciding or trying to work out if something is viable or not. But they're making some decent strides down ITER. Another approach is the inertial confinement fusion reactor. So this has got similarities to the the way thermonuclear bombs work. So if you've watched my video on nuclear bombs, you know that the H bombs, the thermonuclear bombs, these are the 2-stage or even 3-stage bombs where you use an atomic bomb, an A bomb as in a fission bomb. You explode the fission bomb in order to supply the energy to create fusion. And that's when you get the H bomb. So it's like 2-stage process. You do some fission, and then the fission powers the fusion. And the similarity with the inertial confinement technique is that you're compressing material. So if you can compress stuff enough and you can get the density and the pressure up really, really high, then you can get fusion occurring. And this is the process that goes on at the National Ignition Facility in California, the NIF. So you've got a laser, a huge laser, which zaps these pellets of fuel. So you get little pellets of tritium or deuterium. The laser zaps these things, and these pellets, they almost behave like little supernovae. So the outside of the fuel pellet will explode outwards, and the inside will compress under the shock wave. So you've got this conservation of momentum thing going on. So you've got a pellet, the outside flies outwards, and then the inside will implode. It will collapse inwards. And then that collapse, you'll get the density, the pressure, the temperature, it all starts rocketing upwards if you can get it to collapse in the right way and sufficiently violently, and then you'll get fusion coming out of that. So you've got 2 different ways going on here. There are loads of other projects around the world trying to get fusion reactors working, but these are 2 of the big name ones, ITER and the NIF. So I can't remember if I mentioned this is in California in the US at I think it's the Lawrence Livermore lab, I think it is, or thereabouts. So yeah, there's a bit of background anyway on the fusion reactors. There's still work to be done on all of this. It doesn't look as though this is going to be our sudden fix to the energy crisis that we've got at the moment, but great strides can be made if you think of how far physics has come in the last 100 years. Maybe fusion is going to be reality before the end of this century, or maybe earlier than that. I mean, it's very hard to say with these things, but fingers crossed, because it'd be a nice thing to add to the mix going forwards.